In this video, we're going to extend upon the previous video where we defined how we can use Turing machines to decide a language and relax that definition to talk about Turing machines which partially decide a language, or in our terms, semi-decide. And we'll also talk about how we can use Turing machines to compute functions. If you were comfortable with the previous video, the macro language that was used in it and the definitions that we made, you'll be comfortable with this video. So we'll jump right in with a definition of what we mean by this idea of semi-deciding or half-deciding a language. So our definition for deciding a language was that we had these definitions for whether or not a string accepted or rejected, whether or not a machine accepted or rejected a string, and we just said for any possible input string, a machine had to halt and either say yes or say no. In this case, we're going to only require our definition to be that strict for one of the cases. So given some string from the input alphabet of a Turing machine, we say that the machine semi-decides the language if and only if, when the string is in the language, our machine still halts and says yes, but this time we relax the definition for what happens when our string is not in the language. In this case, when the string is not in the language, all we require is that the machine definitely does not give us a false positive. It definitely doesn't halt and accept. The options include, however, that our Turing machine may either reject, just like a deciding Turing machine does, or it may loop forever and fail to ever halt. So we can see immediately from this that every deciding Turing machine fits our definition for semi-deciding Turing machine because they all just reject in the case of a string not in the language. So we can see that this is a relaxed definition. Now we say that a language is semi-decidable if and only if we have a Turing machine that can semi-decide it. So just like we did before with the definition of the decidable languages. And in this case, we have our set of all semi-decidable languages SD. And our big question will be whether or not they're really just the same set. Now, obviously, we do know, very trivially, that all of the decidable languages fit our definition for semi-decidable. So this is definitely a true statement right from the start. But the question is whether or not this is an equality or an absolute subset. So before we go answering that sort of heady question, let's just go through an example of a Turing machine which semi-decides some language. And we're not even going to worry about trying to deal with languages like the non-context free language that we did in the last video. We're actually going to start with something regular. So this regex here, and you should all very quickly realize what that regex represents, and I would recommend stopping before I tell you the answer because it's good practice. But this regex represents the language of strings made up of A's and B's where there is at least one A somewhere in the string. That's all the requirement is. There is definitely one A somewhere in there. Now we can easily build a Turing machine which semi-decides that. We just need to make sure that every time there is a string which definitely has an A, we will definitely halt and accept. And we just need to make sure that we don't accidentally halt and accept if we get a string made up of all B's. So we will define this machine first just in terms of some basic procedural English here, and then so that you can get an idea of how sometimes we'll describe Turing machines just using basic English instead of using a macro language or a tuple definition. So our Turing machine is just going to loop, and every time it moves in this loop, it's going to move one square to the right in the string, so it's going to get to the next input symbol. And if what it sees is an A, it's going to halt and accept. So you can see, as long as while ever it's seeing things that are not A's, it's just going to keep moving the square to the right. And it's going to keep moving even if it starts seeing blanks. So if we have a Turing machine, which we start off with the string B, this is just going to keep going forever, moving to the right. It's never going to halt. So this fits our definition of semi-deciding. You'll note from the previous video that this does not fit our definition of deciding because this is a string that is not in the language, and our definition of deciding said that we had to halt and reject. But in this case, for semi-deciding, it's fine. It can loop forever when the string's not in the language. Now, I'm not going to go through the macro notation because I believe that you should be able to look at this and understand it very simply. But this is a macro notation for the exact same thing, and I'd like you to pause and look at this and make sure that you're happy with the fact that these two things are equivalent. Now, some of you may have noticed while I was doing that would have been very easy to just build a Turing machine which decided the language. And in fact, we know that we can do that because what we started out with was representable using a regular expression, which means it's regular. And we said that we could build a deciding Turing machine for every regular language. So in our English definition again, we can extend it slightly to handle a case where we have strings made up of all b's, which is the only remaining possible, or empty strings, which are the only possible strings that we have to deal with, which are not in the language. So in this case, we loop moving one square to the right, and if we see an A, we halt and accept. But if we see a blank, that means that we're at the end of the string, because our initial configuration is always all of our string made up from the input alphabet, which never contains the blank, and we start with the tape head to the left. So if we move and we keep going and we have not seen an A yet, but we see a blank, we know that the string must have been 0 or more B's. So at this point, we just halt and reject. So, like we said before, the definition of a semi-deciding Turing machine actually the definition of a deciding Turing machine still fits the semi-deciding Turing machines. So it's obvious that if we can build a deciding Turing machine, we should always be able to make it into something like the one we just saw before, which ends up looping forever when we get into rejection situations. And so at this point, you'll notice that the only thing I've really confirmed from our heady question of whether or not D and SD were the same was the obvious part, D is in SD. And I'm not going to answer this question here yet because that's much more complicated and for a later discussion in the lectures. What we are going to talk about is the fact that we had this idea that when we had an initial configuration like this, and we said that this eventually yielded like a halting state of some sort. It's something left on the tape. And we would say this meant that this string the string was accepted or rejected, and we didn't care what was left on the tape. But the fact of the matter is that our Turing machines may leave something on the tape, and we could use that to do something. So we ignore it when we're building our deciding and semi-deciding Turing machines, but we don't actually have to. And some of you may have already realized that we could use this to start computing functions on strings. So if we have some transformation from the input alphabet to some other alphabet, we could build a Turing machine so that it just halted and didn't really worry about accepting or rejecting. It just halted, but what it left on the tape at the end was a function of its original input. And that's what we're going to discuss in the next couple of slides. So with our usual tuple definition here of a Turing machine, and we're going to have our set of halting states H just be one single halting state. So in this case, we don't have two halting states which can tell us yes or no. We just have a halting state which says the machine is finished. So we've got no yes or no answer. Our initial configuration in this case will just be the same as we've got before. We're going to put our input down on the tape and start our machine off one space to the left. And we can define the output of the machine to be Z if and only if our initial configuration eventually yields the halting state with Z to the right hand side of the current spot where the tape head is, and the tape head being at a blank. So if I can start with something like this, and I can use my Turing machine to eventually end up in a situation like this, and my Turing machine state is the halting state, then I say that the output of the machine is Z from given W. Now we know that we've got our input alphabet sigma, which has to be a strict subset of our tape alphabet gamma, which includes the blanks. But we can also have a different output alphabet, and we'll call this sigma dash, which again is some subset of the tape alphabet, but it may not have any relationship with the input alphabet. For instance, we could potentially be considering a definition where we've got strings made of A's and B's and we want to spit out strings made of C's and D's. Now obviously the A's, B's, C's and D's have to be in the tape alphabet, but there doesn't necessarily have to be a relationship between the input and output alphabets. Let's say given an input alphabet and an output alphabet, we can define a function from input strings to output strings, and we can say that our machine computes that function if and only if for any possible input, if the function is defined on that input, then the output of our machine is the same as the output of that function, and otherwise our machine loops forever, because we don't want our machine to spit out an answer on a function that doesn't have an answer for that. So it'll be a little bit like our semi-deciding examples, where if we get something we're not able to handle, we just loop forever. But as long as the input is one that the function is defined on it, our machine has to halt and it has to spit out that answer. We say that a function is computable if and only if we can make a Turing machine which computes it and always halts. So obviously functions which are not defined on those things we're not really concerned about. Another name that you will often hear used for the computable functions are the recursive functions, and those two terms are equivalent as far as we're concerned. The first example we're going to give is computing a function on strings. And it's going to be a pretty simple function. We'll have an input alphabet made of A's and B's, and our function given any string W is simply, the output of that is simply W concatenated onto itself once. So in this case we can see that our output alphabet is equal to our input alphabet. Now our initial configuration is to have a tape head on the blank with our string to the right of it and all blanks after that string. And our expected output configuration will be the tape head on a blank with the string repeated twice after that with no blanks in there, and then blanks to the right. It's important to note that this particular blank spot here and this blank spot here don't have to be the same location in the tape. It doesn't really matter. What we're going to do is actually split this up into a series of steps, and we're going to define some subroutine machines. Much like if you were trying to tackle a complicated programming problem and you split it up into a series of functions that do little bits that you can understand very easily, and you end up with a simpler solution to the problem. That's the same thing we're going to do here. So first we're going to define a copy machine C. It's going to do most of the work by copying the string onto the tape again, but in this case it's going to leave a little blank in the middle here, and this makes it easy for us to tell after we've started copying where the end of the string is. Because if we look at this problem and we just started naively copying things to the end, after we'd copied a few symbols, how would we then know what was the end of the original string and what is the start of the copy of that string? So in this case we simplify that process by leaving a blank. So our copy machine is defined using a macro notation down here. Our machine starts on the blank to the left of the input string, and then it moves right, and if it sees something that isn't a blank, it stores it in our variable x. Then it wipes out that, so it gets rid of it, and then it moves right until a blank. So at this point it'll be here on the end of that, and then it moves right until a blank again, leaving a gap, and it dumps down the thing that it saw before. Then it moves left until a blank again twice, so that it gets back to the start of the string, and it writes that symbol back down again. So in this case that blank here will be where that original symbol was. Now you can see if you follow this through, you'll end up with, for example, follow it through for the string ABB with all blanks, and you'll see that what you end up with at the end is a Turing machine with ABB, a blank with the tape head sitting on that blank, and ABB again. But I would suggest following through that example. Now if you remember from class, we defined this shift left machine, which if it had something if it was sitting on the blank at the start and it had something to its right, it would move that one space to the left with respect to anything that's on the left, but they didn't need to match. So if we have something that does this operation here, we can apply it to the situation like this, and what we'll end up with is something that goes from our initial configuration to almost what we want, but just with the tape head on the wrong side, so we can simply move left until blank. So if we compose a Turing machine made up of sequentially just calling first our copy machine, second our shift left machine, and finally move left until a blank, we'll have something which ends up getting to the final configuration that we needed to say that we had computed the function f. I'm not going to do all of this next function because otherwise this video is going to get too long. But we can consider the idea of computing a numeric function just as computing a function on strings. So let's imagine that we have this function called the successor of an integer n. We can also, if you like, you could call it increment n or n++ or something like that. But basically, given an integer or a natural number, it will spit out the next natural number, so n+1. And we're going to represent n in binary, and we're not going to worry about 2's complement or anything like that. We're just going to represent the natural numbers in binary. And in this case, our input is going to be defined only for natural numbers without leading zeros. So it's an element of this regex here, which you can see, you should be able to see represents binary numbers that do not have leading zeros. So given an input, the output has to be the encoding of the next natural number in binary. So for example, if we have 1111, which represents 15 in binary, the output should be 1 with 4 zeros after it, which represents 16 in binary. What I would like you to do is go through a few examples, particularly looking at the edge cases like 0 or 1 or something with all zeros like this or something with all ones like we've done before, and follow through this Turing machine M here, which does compute that function, and see for yourself that it makes sense. But this is a pretty simple macro language definition, and you'll notice if you're using this that we use a trick about binary numbers which makes it easy for us to deterministically compute the succession function just by treating it as a string of ones and zeros without actually ever having to have an idea of what the value of that binary number is. The final note that I'd like to make in this is that we talked about the idea of functions being computable, or the other word we used was recursive, which just means the same thing. Now, an important question for us is whether or not all functions are computable. And I won't go through that, but here is a good video on a function called the busy beaver function, which definitely is not computable. And here you can see the YouTube video for that. And for those of you who are watching this on YouTube, I'll also post the link to this video down in the information section below. So to summarize the last two videos, we have these machines called Turing machines, and we've shown that they're more powerful than all of the formalisms that we've already talked about, the push-down automata, context-free grammars, regexes, regular grammars, finite state machines. The problem is that they're a lot harder to work with than the computers we actually work with. If you were to go and try and design something using Python or another programming language to do some of the things that you've done before, even if you didn't use a library that did what we were talking about, it would still be far simpler to design bare bones code to do compute functions or decide languages that we've talked about here before than it is with a Turing machine. So it's a bit hard to work with. So what's the point of defining this Turing machine? We've done all of these steps. We've gone from the finite state machines, we've gone up to the push-down automata, we've gone up to these Turing machines, which are now very ungainly to work with. So what's the point? Well, the point is that because these Turing machines are quite simple, which makes them hard to work with, it also makes it easy for us to use mathematics to reason about them formally. So if we can show that Turing machines are equivalent to any other computing device that we have, then if we can formally show that Turing machines can't do some things, then we'll know that real computers can't do those things either. And that's essentially the point of this here with our theory of computation, is to reason about what we can do with computing devices.